right, looks like it's about that time. Thank you all for coming today. It's my pleasure to introduce Stephen Miller from Williams College. He is presenting AMS expects that every mathematician will do their ODEs, from the Battle of Trafalgar to calculus, or Newton to Nelson, or Nelson to Newton.
Nelson to Newton, right. Would be interesting going in the, actually, we probably should go in the other order because Newton was first. But anyways, thank you for the introduction. Thank you all for coming. If you have any questions throughout the talk, please feel free to speak up. I want this to be a discussion because I'm really interested in hearing from other people as to what have they found works, what have they found doesn't work. Just a little bit on myself. I have been at so many institutions, it would take half the talk, I think, to just go through all of them. I've seen everything from large state schools to small liberal arts colleges. I've been teaching for several decades and have been watching the great shifts in what we're teaching and why we're teaching it. And so I'm really interested in people's comments about how they're choosing to motivate certain material, what material they're choosing to put into their classes. And so I want to talk a little bit about how I've tried to move some mathematical modeling, especially through differential equations, into several different classes that I teach. So in case you're not aware of what a liberal arts college is, I know I wasn't until I started teaching at one. We typically have smaller class sizes and we have students with diverse interests. So occasionally I will actually have history majors or English majors taking advanced level mathematics classes, which is wonderful, and it provides an interesting opportunity as to what examples can I choose to excite people, because it's not just going to be people interested in a graduate career in mathematics. And so what I want to do today is I want to discuss some of the opportunities, as I said, to introduce students to mathematical modeling and the different types of examples we can use to excite them. If there are any science fiction fans here, there's some really nice science fiction stories where faster than light travel occurs, and they remark that there are a set of differential equations that solve these. I'm actually trying to talk to the estates of the authors to get a hold of those differential equations and hopefully can present those next year. As I mentioned, I teach at a liberal arts college where I have students with very diverse interests, so I'm always trying to find other examples to use. My go-to examples are typically physics, because I was a double geek, math and physics, as well as sports. I've done a lot of baseball mathematics. And what I love about the topic today is this gives me a nice opportunity to bring in some history. And then I want to really highlight to the students the importance of being able to use mathematical software, not just to solve problems, but in terms of visualizing and using that to help us understand what's going on. How do we present this? A lot of my students go off into consulting and to other real world situations where they have to talk to people, and just helping them learn how do we present the mathematics in such a way that you can be convincing to people who don't know as much as you do, that you can really drive home the key points of what's happened. Okay, so I've mostly done this in certain classes like Calc 2, Calc 3, where it's very natural to talk about differential equations. I've also done it in probability. I've done it in operations research. Whenever possible, I try to work classes like this, topics like this into the classes I'm doing, because the 21st century, with all the data, with all the technology available, one of the skills that we really need our students to learn is how to do mathematical modeling. They don't need to be able to solve them to the level that I needed to when I was trained, because there's so many good software packages out there, but they need to know enough so that they can understand, is the result that they're seeing reasonable, and how can they present this in such a way that it's convincing. So I've done related problems to this, the standard predator-prey that we all do, and then just trying to build on stuff like that. So there's really not too many prerequisites for the Battle of Trafalgar, which is one of the things I really love about this. Calculus 2, Calculus 1, more than enough background for something like this. And so the example for today is modified from Mathematics of Warfare by Lanchester. And I was recently at the joint math meetings, and the organizers were very kind and had me following somebody who had actually just talked about this paper and this model. The presentation today is going to be on a simplified model, but you can of course add more bells and whistles and have it closer to reality. But it's a great way to start. And then of course we can always ask the students, okay, so what would you try to add next, and how would that complicate things? What do you think we can do with this? So for the prerequisites, we just basically need the exponential function and its derivatives, We sometimes do discrete systems depending on how much time I have to build up some intuition, where again, things can be solved, oftentimes in closed form. I don't assume any historical knowledge. I just, talk to the students as needed. And it's always interesting to see, who remembers their, European history from high school or maybe from a college class. So just to put things in perspective, the Battle of Trafalgar was one of the most important naval battles in, the history of the world. It was the British against the combined fleets of Spain and France. And this basically was, one of the key turning points in the war. Massive battle between the fleets of the two combatants. And so Nelson was outnumbered. So he was the command of the British fleet. And the question was, how can he win against, a superior force? And again, as soon as you use words like superior, superior in what sense? Numerically, the other ships, outnumbered his. But then you can also talk about, well, maybe there were more ships, but maybe his ships had better crews, had better weapons. So these become interesting complications that you can start working into the model and ask, well, how can we have a model that takes all of this into account? And so the key idea that Nelson had, and it's sketched roughly in this picture, is to have his fleet come in and split the forces he's facing into different groups. And the idea was to have some of his ships fight a delaying action against a contingent of the enemy, while most of his ships then dispatched one part. And then once they finished, they would then come to the aid of that smaller group. And of course, as soon as you say this, then the natural questions become, well, how should he split up the force he's facing, and how should he split up his forces? What's the best way to do all of this? And can mathematics help? And so in the article, it says, for the purposes of framing his plan of attack, Nelson thought his own force would consist of 40 ships against 46 of the enemy. And he has it initially coming in as 3 groups, 16, 16, and 8, splitting the enemy at the points of 12, 23, and so on. And then in Lanchester's analysis, they talk about what's called the square law, that basically the strength of your forces is equal to the square of your number. And this is assuming that all the ships have equal combative strength. And again, these are now wonderful points for class discussion. Do you believe that this is reasonable? You're assuming that all the ships are equally strong. And then second is, do you think a square law is a reasonable law? And you can talk about the reasonableness of the square metric. And this is one of the key points I want my students to get out of something like this. I doubt any of my students are going to be commanding naval forces in engagements, but this idea of trying to find what's the right metric, what's a reasonable metric, raising something to a power, that's an easy, simple thing to do. And you can try to look at extreme cases. If we had twice as many ships as the opponent versus 10 times as many, well, as we start to get 10 times as many ships, 10 to 1, we might expect to be able to win the engagement with almost no losses. And so this idea of squaring as magnifying the advantage of your numbers, maybe this is a reasonable metric to use. And then the hope is that we can actually get to a theoretical justification of this later. And then you can also ask, where have you seen measuring things by squares before? And then, hopefully, if you have some students who've done statistics or probability, they might mention that in a lot of analyses, we use the sum of squares of the deviations, not the absolute values, not the differences, because differences are signed and canceled, but the square is a natural metric. And so there's a lot of wonderful conversations you can have along these lines. And that's one of my main points in using this example in lectures, is to try to get conversations with students about how do you create models, how do you create the metrics that you're going to use. Depending on what values you care to focus on, you can get very different results. And so if Nelson splits his force into 2 groups of 32 and 8, and then the combined force into 23 and 23, then if you assume this square law, it actually gives a British advantage of 30. Whereas if you don't split, the 46 squared of the enemy ships Nelson is facing versus his 40 squared gives a significant advantage to the French-Spanish fleet. And so again, under the assumption that the square law is reasonable as to the effectiveness of your force in an engagement, we see that a simple split like this is going to result in shifting the tides, if you'll forgive the pun, to Nelson's advantage. And so now we go into trying to understand, how should we model things? And so I am old enough that I remember the old Charlie Brown movies, where nothing ever went right for his baseball team. And so I try to talk about the difficulties in coming up with a reasonable model for the real world. The model should capture the key features of the system, but it should also be mathematically tractable, or at least amenable to simulation in a reasonable amount of time. And these are often very competing demands. And so trying to balance the two and come up with a way to describe what we want to in such a way that ideally we can get a closed form solution, and then we can see as we change the parameters what effect does that have on the resulting solution. If we're not lucky enough to do that, at least we can run some simulations and get a feel for what's going on. And so to write things down, we'll let R of t and B of t represent the values of the two fleets. And so this was done so that no one feels bad. So instead of the British against the French and Spanish, in a lot of the papers, they say it's red versus blue. And so R of t and B of t will be how many red and blue ships we had at a given time. And then we want to come up with some natural models for how the numbers change over time. And so the simplest equation we could write is each one is decreasing. That's why we have a negative sign and positive values of n and m. And the rate at which the blue fleet is decreasing is going to be proportional to the number of red ships. And the more red ships we have, the faster the blue fleet should be decreasing. And n is going to be a measure of the effectiveness of the red ships, and similarly for the blue. This model assumes that you can't have ships created. This is actually a false assumption in the battle. Back then it was possible, and in fact it even happened in this battle, that you could capture enemy ships. And at the end of the Battle of Trafalgar, the British fleet was actually larger than when the battle began. But again, for the simple model, we'll assume that the fleets are decreasing in size as a function of time related to the size of the enemy that they're facing. And so we discuss why this is reasonable, we discuss why this is tractable, and we talk about, are there any special values of n and m that are more likely to be analyzed? And then, usually the students say, well, if n and m are the same, then the model is a lot more symmetric. Although it turns out that it's not that bad if n and m are different. And so, how would we solve something like this? Usually the students realize, well, if we just take another derivative, then we can replace r prime and b double prime with what we already have, and we get a nice relationship for b double prime in terms of b of t, and similarly for r double prime in terms of r of t. We can solve these. These are just exponential functions, and then we can write down the general solution, and then we can ask, are these reasonable? And if so, do we have any idea of what the parameters should be? And again, this is great because it gets the students to be thinking about the mathematics and the resulting values. And usually they quickly realize that, well, one of the exponential factors is increasing, one of the exponential factors is decreasing. We shouldn't have the size of the blue and red forces exploding to infinity the longer the battle goes. So probably B1 and alpha 1 have to be 0. And then at this point, I mentioned that as a consequence of this, we do get this kind of square law about the effective fighting. And we'll talk about that in greater detail in a little bit. So now it's time to start discussing how can we display this information in such a way to drive home what's going on, to explain what the consequences of this model is. And so I was a double major, as I said, including physics. We used Mathematica all the time. So for me, I use Mathematica. Anything you want to use is fine for this. The main thing is to be able to just generate plots quickly, to be able to vary parameters and see what's going on, and then just thinking about what do you want to plot. And so here, I set it up with unequal strength, factors of 2 and 3 for the effectiveness. And I, carefully choose the initial strengths of the blue and the red forces so that as time passes, they are just perfectly balanced and they eliminate each other. And so the first plot is plotting how many red and blue ships we have as a function of time. And we see that they perfectly end up. And then this is a way to kind of check and see, was the square law reasonable? And we see b of t squared over r of t squared is constant. And I can ask them, well, what number do you see it's constant at? And they'll see this is around 2/3. And looking at the numbers, you can see 2 and 3 coming in very naturally from the choices of the strengths N and M, which then of course suggests to the students, maybe the answer is going to be related to N and M, and they can try different values and get a sense of what's going on and get a conjecture for what the relationship should be. So I then talk a little bit about the N-square law in warfare, mention what was going on here, and then just write down some of the differential equations and the solutions, and then try to use this to talk about some other things that they may have seen and try to put some of the solutions in context. So as I mentioned earlier, I love physics, but I also love sports. I love sabermetrics. I've done a lot of work in that subject. I have a lot of students who compete on a variety of athletic teams. And so one of the examples I like to do is, how far do you hit a ball and what path does it take? And so, if you assume that there's no air resistance and you get a really nice parabola and you can see, where does the ball hit the ground at what time? And if you go through and you do the analysis, you see that there's actually 2 times when the ball hits the ground. And it seems a little bit strange at first because, when you hit the ball, it should go forward and then land, and it should only hit the ground at 1 time. So what does this other solution mean? And this is a great opportunity to talk about, when we're doing mathematics, do we introduce other solutions? What do these other solutions mean? Well, when we hit the ball, the batter has some height and he's not hitting the ball, on the ground. He's hitting the ball somewhere above, a couple of feet above. And so what we could do is we could say, let's say that that's times 0. And we have an initial angle of the ball, we have an initial height, and it goes into a parabola. We can run time backwards. And even though the ball does not start at the ground and then come up to his waist, we could say, well, if we were to take this path and extend it, then the ball would have started somewhere behind him at the ground. And that's what the other solution means. And so we can ask, do we have similar things when we look at this model? Well, one of the dangers is to use a formula in a range where it's not applicable. So the big example is, if you ask students to use a geometric series, the infinite formula, they have to remember to check that the ratio is less than 1, or you get something that is absurd. If you keep using the formulas we wrote down for how many ships there are as a function of time, there's a certain critical time where one of the forces, if not both of the forces, is eliminated. And so at some point, let's say the blue eliminates the red, the number of red ships become negative. And so if the battle were to continue and you were to keep using these equations, because it's negative, this would now result in the blue force growing. And so you would start getting absurd answers. And so this is just a great way to warn students that, these formulas only work up to a certain point. And we want to figure out what is that critical time. And so, starting to do, a little bit of analysis to figure out, how do we find what that critical time is. And then just, talking a little bit more with them about, different ways, as I said, to present the information. A very natural question you might want to ask is, if you have a battle between 2 forces, how much of your force do you expect to survive? And so here's a plot of how many blue survived versus how many blue went to battle against a red force of 1 unit. And whenever I show students plots, I always want them to be thinking, is this reasonable? When you look at this, does this make sense? And so here, the solid blue line at an angle is just essentially the line y equals x. This would be, assuming that no blue ships were lost. So this would be the theoretical best that could happen. And then the curve that you see is what you get when you do the mathematics as to, how many ships are left after the battle. And if you look at the plot, the students very quickly realize by, checking extreme cases that it passes the smell test. If you only had 1 blue ship going into battle against 1 red ship, if they all had the same strength, you would expect they would destroy each other and nothing would survive. And you see that when there's 1 blue ship, nothing survives. It's at 0. And then in the limit, as you get more and more blue ships, very few of the blue ships die. And it's going to get very close to this line y equals x. Now, the difficulty, of course, is how close is this the right rate of convergence? And that's a much harder question to answer. But you can at least see that the extremes are close, and this is asymptotically like this. If you're really brave, you can ask if they remember their conic sections from high school where we did the asymptotics for the hyperbolas, And we see, something similar going on here. The next plot, which I like to do to just see who's really paying attention, is, here's a plot of how long it takes a blue force to wipe out a red force. And so the vertical axis is the size of the blue force. The horizontal is the time it takes to wipe out one red unit. And asking, is this reasonable? And so, if you think about it, so the vertical axis is the size of the blue force, and the horizontal is how long it takes to wipe out. So as we start to get a larger blue force, it should take less and less time to wipe out a red force. As we get less of a blue force, it should take more time to wipe things out. And so, the claim is the horizontal axis is the time it takes to wipe out. Well, once we get below 1 unit, we shouldn't have the blue force wiping out the red force. There's something wrong here. This plot can't be right. It fails what's going on in the limit as we go off to the right. And I'll leave it to you as an exercise to figure out if things are reasonable as we go to just having the file left of the plot. And I like to include this because there's often typos, there's mistakes all the time, and I want my students to get into a questioning mode, not just to assume that whatever they have is correct, but to really look at this, run some tests, see, is this reasonable? And so the correct label is it's a plot of how long it takes the blue force to wipe out the red force. The vertical axis is the time it takes to wipe out one red unit. The horizontal is the size of the blue force. So the bigger the blue force, the less time it should take. That makes sense. And so, this is the correct plot to see what's going on. I'm a big fan of XKCD, and one of my favorite strips is two people are talking, and one says that we should break up, and I've got the data that can prove it, and gives a plot of the relationship, and the person agrees and says, I knew the data would convince you. No, I think I can do better than someone who doesn't label their axes. And if you click on an XKCD comic strip, it gives you additional data, an additional joke. And the additional joke here is, and if you labeled your axes, I could tell you how much better. There's a lot of work that's done to manipulate plots. I saw a great plot about, how much gas prices had fallen given a certain policy. And things were zoomed in so greatly that a small change looked enormous. And so I really want to emphasize to my students, the need to provide plots. And just saying a few words is not the same as giving you good labels to the axes as to what's going on. They really want to think long and hard about what information are they presenting, how do they want to present it, how do they want to put things in context. And then the last thing, for projects like this is asking students, well, what could we do next? And so there's, lots of things that we can do in terms of, future things. There's lots of questions. One of my favorites, of course, is, trying to figure out how do we want to optimize? How do we want to split things? And, the simplest is trying to set up the calculus problem for we're splitting our force in two to split the enemy in two. And try to figure out, where do you want to do those splits to maximize things? But of course, you could also try to split things into 3, into 4, into 5, and try to figure out, what's the best way to do that? How many splits do you want to do? And then just to, put things in perspective, the final result was, far different than the mathematics would have indicated. It wasn't just a slight victory for the British, but the British lost 0 ships and even captured some of the ships from France and Spain. And then just the aftermath of the battle, so we've seen how we can do some very simple mathematical modeling. We've seen how this modeling can have real-world consequences, but we've also seen that there's a lot of issues with this modeling. And so one of the biggest issues is this is completely deterministic. There's no luck that can happen. There's no anything like that. So can we incorporate somehow random variables? And at this point, of course, we're no longer going to get closed form solutions, but can we maybe put in some random variables, run some simulations, and see what happens most of the time? How sensitive are things going to be? How likely is it that you're going to be very exposed and something could happen? And so this leads to stochastic differential equations, and there's just so many other wonderful things that you can talk about. So thank you very much. I look forward to if anyone has any comments or suggestions of other things that could help make this more effective when I'm trying to introduce my students to mathematics in the 21st century. now that we have so many packages that can solve these questions, present the information, it's trying to teach my students how to be good mathematical modelers. So thank you.
Hi, Stephen. It was wonderfully interesting, stimulating talk. I had a question. In the beginning, you'd mentioned that you would consider discrete systems as prerequisites. And I was wondering, have you modeled this system discretely? And if you might comment on the pros and cons of differential equations versus difference equations in terms of predictions, and also how easy it is for the students?
So as the president-elect of the Fibonacci Association, I have to publicly come out in favor of difference equations and just how absolutely wonderful they are. But I've actually never done this particular problem with difference equations. It's an interesting question. I mean, do you want to say that the ship either exists or doesn't exist, or do you want to say a ship has a continuum of strength from 100% to 10% and is still able to fight? So I think for this problem, I think this is a perfect question that I should have been asking, and I'm glad because I will now ask it going forward, is we should always ask, are we doing the right model, or are we doing a model that is easier to do? So I have some nice papers with students on the Pythagorean one-loss expectation in baseball to try to predict how often a team wins. And we use a continuous model for runs scored and runs allowed, not because, as much as I'd love to see the Sox win a game against the Yankees by a score of pi to e, I think that's going to happen, but because the tools of calculus are available. And so sometimes when we're going for closed form solutions, difference equations do have nice closed form solutions as well. You can set up these modelings as well. I think that's a great question, and it would be interesting to just see how different things are if you try to do it continuous versus discrete. And then the question is just, does a ship all of a sudden instantaneously lose its effectiveness and become zero, or does it slowly fight? Or here, would you almost want to have like the stochastic, where you would have a continuum of possibilities for what can happen to the ship? Is that depending on how bad the hit is, the ship may be able to function for a while, but at reduced strength.
Thank you.
So,
yes, thank you.
Well, I would like to hear the prediction about the Yankees.
I'm sorry, did you say something I wasn't able to hear?
I said that I would like to hear the prediction about the New York Yankees.
So if you email me, I'm happy to share my stuff on your baseball modeling. So it's SJM. I'll just put this to everybody.
As long as they are winning, I'll take it.
I will take it as well. I am not greedy. And so what's interesting is the model I came up with was inspired by some physics classes I took, is trying to figure out what's the probability you score more runs than you allow. And because there was a closed form that was conjectured, I was trying to figure out what would be reasonable runs scored and runs allowed distributions where the resulting double integral over the triangle where x is greater than y would have a nice closed form solution as a function of the parameters. And so there again, the hope is that we can come up with a model that's simple enough to do in closed form that is still a reasonable approximation to reality. And what's nice about the closed form solution is you can then answer questions such as, I know if I score this many runs and allow this many runs, this is my predicted probability of winning. I have so much money to spend in the off season. Do I want to spend more money on batters or on pitchers? How much will this batter contribute to my runs scored? How much are they worth? And so when you have closed form solutions, it allows you to make really good predictions of how you should allocate your resources. And to me, this is a question that resonates with a lot of my students who are about to go off into consulting.
That makes sense. But I have come to the conclusion that if you score more runs than your opponent, you win.
Yes.
That was nice talk. I think we applied. Okay, to tell you the truth, this is the first time that I see mathematics applied to warships the way you present it.
Well, so again, this is not original. I am giving full credit to Lanchester. It was absolutely beautiful article. Very accessible, and again, this is something that I think can excite students is to see. I mean, I had a student who was actually taking the class with me while he was taking a class in European history. He's like, "Hey, can I try talking about this to my?" I says, "Go for it." I would love to see the European history class dealing with differential equations.
Nice talk.
Thank you. Have a good one, all.
Thank you.